Hi everybody, and welcome to the SEAMS forum on additively manufactured metal surfaces and their influence on tensile and fatigue performance, to be given by Professor Ma Chen from RMIT University. For those of you who don't know me, my name is Milan Brandt. I'm from RMIT University. I look after the additive activities at RMIT. And I'm also a CI within the SEAM Centre that's led by Professor Chris Burnt. SEAM is an ARC-funded, Australian Research Council-funded training centre. We have something like 20 PhD students, a number of industries. There's something like 12 industry projects. And RMIT is leading one of the projects that myself and Ma are involved in. So a little bit about Ma. So Ma currently holds a distinguished professor appointment at RMIT University. His research is centered on metallic materials and their manufacturing by various processes, including additive manufacturing, solidification processing, powder metallurgy, de-alloying, and deposition. With his team members and collaborators, he has published 240 journal papers and 62 other articles, which have attracted nearly 10,000 Scopus citations. He's a highly ranked metallurgist based on a published study of the research impact of authors' outputs in Scopus from 1996 to 2017. So before Ma joins us, I'd just like to basically let you know that if you have any questions, please submit them online. And at the end of Ma's presentation, Vesna will read the questions out for Ma to address. So on that note, Ma.
Okay, thanks Milan for the introduction, and good afternoon everyone. Thanks for coming to this SEAMS online public seminar, and it's a great pleasure to have this opportunity to discuss additive manufacturing. I guess some of you are very familiar with additive manufacturing, but may not probably. I think after today's discussion, you would better appreciate the challenges we have in handling metal additive manufacturing. So I'll manage to finish my talk within 30 minutes. And today my presentation would focus on the additive manufactured metal surfaces and their influence.
Sorry, Ma.
Yeah.
If possible, would you mind stop sharing your screen and reshare?
Okay, that's fine. So let's redo that. How about this one?
That's great. Thank you very much. Apologies.
So should I restart the process?
You're right to continue now.
Okay. So yeah, today my talk will focus on the additively manufactured metal surfaces and their influence on tensile and fatigue performance. I would mainly use titanium 64 as an example. And first of all, let me acknowledge the funding support from the Australian Research Council. The experimental work to be presented in the second part of this research was all funded by Australian Research Council. And then I would like to acknowledge my team members, Dr. Yin Singh, and my colleagues and RMIT, Dr. Julie Lambs-Bassi, Absira, Professor Martin Leary, and Aaron Petras, and distinguished Professor Milan Brandt, and also my collaborators and CSRO and Stephen Galizia, and Dr. Darren Fraser, and also Dr. Chris Warbrink and Dr. David Monk from DSTG. So in today's talk, I think I will give an introduction to the metal additive manufactured surfaces, and then I will focus on some experimental work, mainly about the influence of the surface condition on additive manufactured titanium 64 properties, including the tensile properties and the relative importance of the surface condition and the internal defects on the mechanical properties. After that, I'll give a few points of concluding remarks. I would like to use this example from taken from the internet, from the Bugatti video released on the 2nd of February of 2018. This is a well-established and titanium 64 part is a brick caliper manufactured by FM 500 using 4 lasers. RMIT has this FM 500. We use that to make a number of parts as well. This is the part of the building on the build platform, and this is the finished part. You compare the surface; they are definitely very different. And what I would like to emphasize is that when we look at a part like this, we all know that many additive manufactured parts have complex geometry. So we don't have many horizontal surfaces. Most of the surfaces, as you can see from this part, they are inclined. So being inclined, well, that means a lot for additive manufacturing in terms of the surface finish. I'll show that later on. This part, I think, it has been well tested. May have been installed in a few Bugatti racing cars. I'm not too sure about that. This is the, as you all know, that this is the support, and we need to remove the support. And this the surface that's connected to the support, we call that downward facing surface. And as you can imagine, after we remove the support, that area of the surface could become fairly rough. So let's look at the next one. So having discussed the surfaces we have on the real part, and in building the metal part by additive manufacturing, we have all these different type of surfaces. And we have the vertical one, we have the internal one, we have the slot. The horizontal one normally is limited. As mentioned earlier, we don't have too many horizontal surfaces. We have the upward surfacing, we have the downward facing surface. And also we have the internal downward facing curved surface. And that would be the build direction. The surface finish, the surface roughness is all different. As you can imagine, let's look at this layer. That's the width of this layer when we do that. Compared to this area, that's the width of that layer will be much shorter than this one, much narrower. And again, because of that, and the heat input and the heat dissipation will be all different. So it's all about the heat and the energy input. So what this shows is that, so when we have a different surface and a different internal feature, and the neighboring, the surrounding environment, or the part bed environment in contact with this particular part of the surface would be all different. And that would lead to very, very different surface finishes. Let's look at a few examples. So this is probably the typical example of the FRM titanium 64, the side surface. The side surface means probably the vertical one, or some outward facing surface, upward facing surface. That's typically this. As you can imagine, there are a lot of particles there. When we discuss surface roughness, we can probably regard all these attached particles. These particles, some of them are well centered, some of them are attached, but not so easy to remove them. we could call these particles as the so-called secondary roughness. And this is the flow pattern. That's really the acidified surface. We could call that as the primary surface. I'll discuss that later. And this is probably the enhanced view of the area from the by modeling from the real surface. Yeah, you can see the surface structure is quite complex. It's difficult to describe such a surface. And this gives you an example of the different type of surfaces. That's the horizontal one. That's fairly smooth. And this one is made by selective electron beam melting. That's the inclined one, and 55 degree, and that's the vertical one, is 90 degree. So from the horizontal to the inclined to vertical, again, that change the, or we can say dramatically change the surface morphology of the surface structure. So let's have a look at the real part. That was published by in 2017. Another good example to show the influence of the design on the surface finish. This is not a titanium part. It's an aluminum silicon tin magnesium waveguide made by selective laser melting. It's using a US M270. That's the internal structures of this waveguide, and that shows the cross-section view. And this is the part when it's built on the plate. And of course, support structures are used again. This is the internal part. And if you can see this one, and then that's the downward facing surface. Internal downward facing surface. You can look at that, the very, very rough surface. Unfortunately, I think this part is not subjected to cyclic loading. As you can imagine, if this is subjected to cyclic loading, this could become the weakest part of the component. That could become problematic. The surface finish is quite different, and it's mainly due to this part being downward facing surface. And this is probably another example, good example. In additive manufacturing, we can call this, that's the build direction. This part we can call an overhang. And this is the part bed and all the part particles. When we build a part like this, or when we build a part within a local structure like this, as you can imagine, and this area of the particles, due to the heat, that will be overheated. And these particles will begin being centered or attached to the surface. And as time goes on, this could become very, very serious. And let's look at this real example published by another group. This angle is 15 degrees. That's the inclination. And this, the resulting surface. When we handle molten metal, or when we do casting, melting the metal, we use this jaws formation on the surface of a liquid metal. And in additive manufacturing, we also use this term, jaws formation, but it refers to a different phenomenon. And this part is the center particles, or the attached particles. This, we call them also jaws. It's jaws formation. And that could change the dimension of the original design. It's pretty serious. This is a good example. So jaws formation here, that's mainly due to the heat, and bear in mind that this is a powder bed. And if we look at titanium 64, the density of this porous material is 2.4, 2.6, and its thermal conductivity is pretty low. Of course, in the case of titanium, and its heat conductivity, thermal conductivity for the pore-free solid titanium-64 is very low. That's only about 4% of that of copper, and for the porous one, it's fairly low and isolating the part effectively. So that's another very severe observation. So if we look at a selective laser melting, these are I hope they have covered this diagram has covered the most important factors that affect the development or the formation of the surface or surface finish. So there are factors that from the FRM process itself, for example, the layer thickness and the feedstock particle size distribution, the laser parameters, the scan strategies, that's very, very important. The position of our part on the platform, and also don't forget the gas flow, and also our ricotta. And also when we slice our part from the STL file, that could have started affecting the surface finish. And if you look at the design features, we have the overhangs, the internal channels, the slopes I showed you earlier, the vertical surface, the side surface, the top surface, the inclined one, the corners. Inclined one are always problematic. And also we have the positive slope, we have the negative slope. That refers to the upward facing surface and downward facing surface. Then we have this, of course, many macro features and support structures. And although people are trying to get rid of the support structures, I think the common practice still have the support structures. And we wire cut them after the additive manufacturing. That would significantly change the surface finish. So this is part of the effect issues. So having discussed the surface finish, and you can appreciate and how challenging it is to manage the surface finish. Of course, you can argue that we can do machining, we can do post-AM processing. It's not always straightforward, and there are features which are difficult to handle. And also, in quite a few cases, and we could just use the parts straight away after additive manufacturing. I think a significant number of the titanium-64 medical implants have been used without significant surface post-surface processing. So effectively, if we would like really to control the surface finish, and we do need to use different parameters or different strategies to build the surface. For the top surface, if we look at the energy input, and we look at if we use the term energy density, which may not be very accurate, but that should be the lowest one. And the bottom one, the vertical one, basically we need to consider the different issues, and that could significantly affect the surface finish. Then we will adjust our additive manufacturing process. Then might slow down the build up a little bit, but once everything has been well programmed, I think we can still significantly improve the surface finish. So that's the next part. We'll show you how the surface finish will affect the influence, will affect the properties. You could better appreciate this the considerations here. So the next question is then how we characterize or quantify mass build surface by additive manufacturing. Well, that's the big challenge. I think that remains to be a big challenge. As you can appreciate, the surface is quite complex. It's almost not possible to use one or a few single parameters to characterize the entire surface and to correlate the surface with the mechanical performance. We'll have to do the 3D, I think, characterization basically using a high resolution micro CT. That's one issue. And once we have extracted the image, the information from the 3D micro CT, and then we can reconstruct that, and that might give us a good description of the surface. Having said that, this surface is very local. That is, the surface features will vary from one area to another. So in that regard, it's still very demanding to quantify the large surface or the entire surface of the part. Is due to I think the cost is also high. And I think we know that the surface area is very important for a number of sectors. And it's interesting to know that some of you might be familiar with the COMSOL multi-physics model, and that software tool, I think, is becoming more and more powerful. That can generate on a surface which is pretty similar as build titanium surface and other metal surface. In that regard, I think the use of this multi-physics software tool may help us to better handle the surface of additive manufactured metal, and to correlate the surface topography with the mechanical properties. I think that's one. And I've taken one image from the Wikipedia, and this is about the geomorphology. And I visited this city, Utah, and sorry, not the city, yeah. There are people who are in other fields who also manage to describe the surface morphology for every of different landscapes of various types of surfaces, or including in the biomedical areas. So I think it's not only limited to the additive manufacturing community. I think probably in the near future, and researchers from one of these fields would make a breakthrough so that we can better describe the surface of additive manufactured metal. The next part, I think I would focus on some of the experimental results. The test coupons used in the following part of my presentation are all from the selective electron beam melted parts. I'll talk about the surface characterization first. And earlier I mentioned that it's challenging to quantify the AM surface using just a few simple parameters. Unfortunately, we have to do that, and it's costly to quantify the entire surface via the three-dimensional approach. So in that regard, I have just used two conventional parameters. It's the RA and RZ. That's probably that describes the depth. And we all know the RA, and the RZ more refers to the depth of the defects. And in terms of the coupons, I mainly used the titanium 64 samples manufactured by selective electron beam melting. There's good reason for me to choose these samples rather than selective laser melting. That's to exclude the influence of residual stress on the tensile fatigue properties. We all know that after selective laser melting, after normal or typical selective laser melting, there's a high level residual stress in titanium 64, and that residual stress can probably mask the influence of the surface finish, or make the results more complicated. So by using the samples made by selective electron beam melting, we can avoid having the ore mining can effectively exclude the influence of the residual stress. There was a piece of careful research done by Oak Ridge, a group from Oak Ridge. They carefully studied the influence of characterized the residual stress in titanium 64 additive manufactured by the selective electron beam melting. They concluded that the residual stress is negligible, effectively is in a full stress relief state. I think that makes sense. If we look at the selective electron beam melting, I think that's commonly accepted. This temperature was measured from the bottom of the build plate, and the actual temperature of the part is higher than this temperature. As you can see, then over the 35 hours of additive manufacturing, the minimum temperature is about 480. That's above that, and the 480 is the minimum required stress relieving temperature for titanium 64. So in that regard, the residual stress should be pretty low. Managing by time, and so then we first look at the influence of the surface conditions on the tensile properties of titanium 64. And in this example, we look at three surface conditions. The first one is as fabricated. The RA is typical in the range of nearly 40 micrometers for selective electron beam melting. The RZ is tremendous. It's quite significant. This parameter has a highly detrimental influence on the fatigue performance. I'll show you later on. Then we use the chemically etched. It's the mixture of the hydrofluoric acid and the nitric acid. And then we have this machined one, and that gives us good surface finish. This range of surface finish in RA and RZ is very similar to the surface finish for selective laser melting. So you could argue that, if you can accept that, this condition may somehow represent the surface condition of selective laser melted titanium 64. Of course, it's different, not so many attached particles. So that shows just show you the surface finish we have, and this is the as-built state. That's the magnified view of the as-built surface. Just now, closer inspection of the as-built surface. Now, after chemical etching, it's not highly smooth. We can see a lot of shallow dents, but we have removed most of the particles there. Removed most of the sinter attached particles. That's the difference between the as-built one as the chemical etched one. This is the after machining. That's really nice, but because the depth of the surface layer we have removed is, and they can still see some piece or some shallow dents there. So these are the mechanical properties. This part of the work was published a few years ago. I think was nicely appreciated by the colleagues in the field. And so this is the tensile property of the as-built one. And it has this group of samples. The as-built samples have a lower strength and a much lower tensile elongation or tensile ductility. And for the machined one and the chemical etched one, they both showed much higher tensile strength, and particularly double the tensile ductility, the elongation. And between the machined one and the chemical etched one, they don't show much difference. That's the interesting point. That is acceptable, and that is up to a certain level, the imperfections on the surface will not affect the tensile properties that much, or the tensile properties are not so sensitive to the surface conditions when the surface finish is up to a certain level. However, they would tremendous influence on the fatigue properties. So that's about the fatigue. Sorry, about the tensile properties. Next one, I would like to focus on the fatigue properties. I have about 4 minutes or 6 minutes, and I really want to look at the relative importance of the surface imperfections and the internal defects. And originally, the motivation came from the medical implants, or the design for the titanium 64 implant parts. You probably know that there have been significant applications of titanium 64 implants made by selective electron beam melting. So if we look at the young adult, if he or she walks 10,000 steps a day, if we aim for 15 years of service of the implant part in the patient, then the expected minimum fatigue strength would be 50 megapascal. And however, we know our human body is very aggressive. It's a very corrosive environment. So in that regard, it's much more severe than the fatigue testing environment in air. So in that regard, in order to ensure this 50 megapascal fatigue strength, the actual implant part we put in should have this level of the fatigue strength. There's not much robust clinical data, but this is based on the implant, the fatigue strength of the as cast stainless steel implant and as cast titanium 64 implant part, both with machine surface. They have that level of fatigue strength, and after being implanted into human bodies, they seem to work well. I said earlier, the information is not highly accurate. And then we look at the surface finish. I mentioned that many of the implant parts don't seem to be to have all machine surfaces, and also for other applications as a motivation from another area. And we work on a project where the application would require just the straight away from the build platform, even without stress relieving and without any post AM surface finishing. So this diagram and this prediction refers to the way of a good surface finish. For example, after machining, it's not homogeneous surface finish. It's not something like as build surface, we have so many sintered particles. If we look at a normal machine surface, a homogeneous surface, and there's a critical RZ value, which is about 2 micrometers. Below 2 micrometers, the fatigue strength would become relatively insensitive to the surface RZ value. But above this value, as you can see, and the decrease is in the fatigue strength is exponential. And earlier I showed you that the RZ value for the EBM build titanium 64 was over 200. So it's normal for nice build surface to have an RZ value around 100 micrometer or even more than that. Or on the surface, there are few areas which could have a high RZ value. We don't need many. If there are only a few areas which have a high RZ value on the surface, that would be detrimental enough to decrease to reduce the fatigue property. So, as you can see, that would lead to very low fatigue properties, and would probably make them not eligible from a design perspective. So that's why we look at this one, and in this part, there's not a new science at all. I think in terms of the influence of the surface finish on the fatigue performance, people have explored that. However, from the practical application perspective, there are still some issues which need to be clarified. For example, the relative importance of the surface defects to the internal defects. We know that definitely with and without the surface finish, surface defects, the fatigue properties would show a big difference. Now let's look at this example. In this situation, we have 4 different types of surface finishes. A is the as-built one, and B again after chemical etching, and C we have the normal level of machining, and D we have a precision machining. It's excellent surface finish, and then we have a large batch of surface, a large batch of samples like this without hot isostatic pressing, and similarly, we have a large batch of samples of these 4 different surface finishes, but with the 2-step heap treatment in order to eliminate the internal defects, so that we can compare these 2 batches of samples to determine the relative importance of the surface finish to the internal defects. As you can imagine, this is a very costly research, very costly project. It took a long time, and these are the 4 different types of surface finishes. You have seen this earlier. That's the second one after chemical etching. That's after normal machining, because the depth of the surface layer that was removed by the normal machining was insufficient. We can still see some defects there. This is really after the deep machining, deep precision machining on the surface is beautiful, and effectively is free of visible defects on the optical microscope. So let's say that we have these 4 different types of finishes, and with and without the 2-step significant heap treatment to remove the surface. And if we look at the RA and RZ value in the as-built state, the RZ value is still pretty high. It's 162. The RA is 31, and after chemical etching, we reduce that RA to 9. Good reduction, but it's still high. And then we have the RZ value reduced a lot. And this is after the normal machining, significant decrease to 0.13, and also dramatic increase to 0.95. I'll show you that it's still not good enough. I think probably due to the surface defects. And this one is really the excellent one, and 0.05 and 0.45. And this gives the experimental data of managing my time, and gives a good summary of the experimental data. For those who are unfamiliar with the titanium silicate 4, we have this envelope is established for raw titanium alloys, and this is probably for the data were obtained from the samples made from the conventional manufacturing with all good machine surfaces. And then this is the as-built one, you look at the Aspiro one, they have a very low fatigue properties, and 300 megapascal is only about 40,000 cycles. So we just we didn't continue with this for the 10 million one, even on the lower stress. It was not worth doing that. That's for the that's build one. For the edged one, that has improved a lot, but still insufficient. Chemical etching has improved the fatigue strength of the build one significantly. Then we have this machine one. This is the machine one. I think, yeah, I'll use 5 more minutes. The machine one, because the surface I showed you earlier, although we did the normal machining, the depth of the machining was insufficient. The fatigue properties were actually close, very similar to the as-built one. And then we have this machine 2. That's a machine 2. That's the beautiful surface finish. As you can see, with the machine 2, the high surface finish that has already entered the envelope of the wrought alloy, wrought titanium 64. That's very, very encouraging. This red hollow circle triangle diamond, that's after heaping. After removing the internal defects, that gave us a very, very interesting comparison. And if we compare this area, the major conclusion is that, and for example, that's heap plus machine 1. It doesn't show too much difference. That's the black solid triangle, red hollow triangle. They don't show much difference. That is the 2-step significant heap treatment doesn't show too much difference, or doesn't increase the fatigue strength much, and it's similar. Also for this edged one, is a bit different. But overall, with all these 3 surfaces, all these is the as-built. We don't have as-built one, the machine 1 and the chemical etched. Applying a significant 2-step heap treatment have not really, by eliminating the internal defects, have not really improved the fatigue strength very much. And the major improvement of the by the eliminating the internal defects comes from the last group, that is with a beautiful surface finish, with a fine surface finish. That's the machine 2, and this one, as you can see, that they can even be clearly above the wrought alloy. So, and also can reach this 10 million cycles. So an important conclusion is that this heap treatment is probably only absolutely necessary when when the sample has a sufficient surface finish. Without a sufficient surface finish, it's probably not worth doing that. On the other hand, having a good surface finish like this one is far better than having an insufficient surface finish plus heap. So just having a good surface finish without a heap is far better than having an insufficient machine surface with a heap. So that's very, very significant. The information here is very rich, and I've summarized a number of good points, but I think that today I'm not going to repeat all of them, but this summarize the difference we have at 600 megapascal. That's the best fatigue property we can achieve. That is excellent surface finish plus 2-step heap treatment. That's the difference between if that's the benchmark, the best one, wrought alloy, or this good surface finish. That's what we have achieved with the heap plus machine 1. That's fairly low. And that's what we have achieved by applying heap and edge. And it's much lower. That's machine 2. That's without a heap. Machine 2 turn out without a heap turn out to be the second best compared to the other combinations. That's machine 1, and the edge, chemical edge, as the build is here. So you can see that I think probably the selection of or the application of heap and yes, probably need to think about that again, and whether our component will have an area which has awful surface finish or not. If that area is a highly stressed area, has very poor surface finish, and then the crack initiation may start from there, and that could be very problematic. We look at the fracture surface or finish in 2 minutes. Look at the fracture surface finish, then all come from our expectations that the surface, the cracks all started from the surface or the subsurface layer, and this is the exception. That is the that's the well finished with the well finished surface, and we don't see any without a heap. Without a heap treatment, we don't see any crack initiation from the surface, and the cracks. And the fatigue cracks actually it started from the internal. That shows a big difference. So I'll skip over the summaries, and I think go to the concluding. I think it's interesting. I missed the concluding remarks, but anyway, I think in having said that having discussed this influence of a surface finish and the properties of the influence on the mechanical properties, I think it remains demanding to characterize the surface. And I think the best we can do, probably we need to characterize all the tangible from the as-built surface, the tangible particles first, and then that refers to the secondary surface roughness, and then we characterize the primary surface roughness, and the good quantitative description of the surface. I think we have to use the 3D approach, and we need the 3-dimensional information. And in terms of the design, we definitely, if it's practical, we need to avoid as much as we can the downward facing inclined surfaces, and then for building, if we have to build those surfaces, as I showed earlier, I think we need to use different strategies. That's probably in a brief summary of my presentations. And finally, again, I would like to thank everyone for coming to this SIMS seminar, and I would be very happy to have some discussion. Thank you.
So thanks very much, Ma, for that very informative talk and practical talk as well. So maybe I'll hand over to Vesna, and Vesna, if you can read the questions for Ma. There are a number of questions, Ma, so maybe Vesna will read them, and if you can respond.
Oh yeah, sure.
Thank you, Ma. Thank you, Milan. Ma, we have Chris, who is interested in knowing something about the starting powders. For example, morphology, size distribution, market costs, and others. Over to you.
Oh, thanks, Weston, thanks, Chris, and I'll give some information, and Milan can probably add a bit more. And for the powder bed additive manufacturing for the selective laser melting, typically we use spherical powder particles from about 20 micrometers to 45 or 50 micrometers. They are all spherical. And then for selective electron beam melting, that can allow the use of much coarser spherical powder particles. It's from about 40 micrometers to 140 micrometers. In that regard, regarding the cost of these spherical particles, Chris, you know that this, and I think for the metal powder production, for the time being, people use metal wire with the plasma atomization to produce metal product for additive manufacturing, and use gas atomization. And generally speaking, the price of the fine powder, which means the size range of 20 micron to 45 micron, is clearly higher than the price for the spherical particle powder from 40 to 140 micron. That's related to the powder production process, where the percentage of the fine particles, fine powder, when I say fine powder, always refers to the size range of 20 to 45 micron. That percentage is not great, and probably the process I know, which has really worked well, that process has achieved about 55% of this fine powder. So the rest can be used for selective electron beam melting or for laser powder deposition, and that's another big market. I hope I have answered all the questions.
Yeah.
Thank you, Mark. Now the next question is, does the thermal spray conductivity of the metal powder used significantly affect the degree of dross formation? Over to you, Mark.
Oh, that's a nice question. I think for thermal spray, I know here Chris is a great expert in that regard. For additive manufacturing, this dross formation is mainly related to the design of our part. And we need it's for additive manufacturing, it's related to the inclination angle and the build height. So it's all about the downward facing surface, and that in that area, because in the powder bed, it's effectively loose powder particles, and we have measured the so-called packing density of the powder particles in the powder bed, and from the selective laser melting process, it was done by Milan, myself, and my colleague Ju and Aaron. We haven't published that yet. Then a packing density, or well, let's say that normally powder density is not high. For titanium, is about 60% maximum of this, or even lower of the powder. So for titanium 64, as I mentioned earlier, the thermal conductivity of pore 3 solid titanium 64 is poor. It's only about 4% of that of copper and so it's in that regard, it's also related to the material or the alloy itself. Clearly, the better thermal conductivity of the material, maybe the lesser, and the occurrence of the degree of occurrence of the joist formation. For the thermal spray, I think if you can design that properly and manage the thermal conductivity, if it's in a molten state, I think you can probably well get around that. I hope you can achieve that. I've seen some beautiful parts made by thermal spray that surprised me. Yeah, it's a great process. Yeah.
Thank you, Mark. The next question is, what is the target surface roughness for titanium biomedical implants?
Oh, that one I think is a nice question, and I'm not sure we have the enough clinical data to support any conclusion. And it's an interesting question, and as far as I know, many of the medical titanium CD4 medical plants, they are just used in the as-built state. Having said that, the surfaces of those medical titanium CD4 medical implants would have, I think they have all those sintered particles. And of course, if somehow those particles come off the surface in a human body, that would be very problematic. That's a potential risk in my opinion. And to completely remove those particles, we need a machining. But for the internal features, internal surfaces, it's not that easy to do that. Particularly some medical parts are very small. And if we look at that, and if you look at the RZ value of the medical implants, and the RZ value is about 200 micrometers. I can probably give you one example. Yeah, okay. And the RA value, I think for the rough surface, if we look at the rough surface, it's probably in terms of RA value is about 20 to 60 micrometers. In terms of RZ value, I think it is up to 200 micrometers. That's probably the best answer I have. But don't forget those attached particles, sintered particles on the surface. Thanks.
Thank you, Mark. Question. Has the influence of surface finish on fatigue performance been yet properly acknowledged in industry? And is it common practice to machine these parts?
Yeah, another good question. Yes, the influence, as I mentioned earlier, there was no new science in my talk, mainly because the general influence of the surface finish on the particularly on the fatigue performance has been well recognized. And I'll put it this way: for fatigue demanding applications, and my opinion is that yes, we have to use the part with the machine surface. In that regard, when we design that part, we have to think about are there any hidden surfaces and internal surfaces which are difficult to machine or to post-process, so that we can avoid having those potentially risky or weak surfaces. So that's part of the design job. Basically, yeah, for the fatigue demanding application, we do need to machine the surfaces. Or, as I said earlier, if we look at the the application for the implant part in the human body. The expected minimum fatigue life is 50 megapascal. If they are built apart by managing the surface finish through design, through the manufacturing process, if we can achieve more than 220 or 200 megapascal, then that would do the job without a surface, without a post AM surface processing. Yes.
Thanks very much, Ma. And look, I'd just like to thank the audience for their involvement and for listening to this presentation. And look, I hope to see you at the next presentation that's organised by SEAM. And I think Vesna will be in touch with all of you. So again, we'd like to finish on this note. Thank you all very much for participating. And thanks, Ma, again.
Yeah, thanks, everyone.
Okay, bye-bye.